Reading, editing, and moving files manually can be great if you're working with a single file at a time. But what if you want to make changes to multiple files? That's where we want some automation. No one wants to rename 1,000 files manually. In this course, we'll look at how to automate many different file operations with Python 3. Python provides built-in functionality for creating, reading, and writing to files programmatically. These operations can be useful for aggregating data across multiple sources, as well as saving out programmatic results to files. We'll also look at how to use the built-in functionality from the Python standard library and leverage other external libraries for manipulating CSV and PDF files. With a file system, we can store and organize files on a storage medium, such as a drive or memory card. Usually, we use a GUI, or graphical user interface, to interact with our file system, clicking into folders or on files to view them. The Finder on Mac provides us with an easy interface to view our folders and files. To create or modify a file, we'll often use another program, such as Microsoft Word or Sublime. These programs must communicate with the file system in a programmatic way so that the work is actually saved to your machine. You can also create programs that read and write data to files. However, to work with the file system efficiently, there are a few essential concepts to understand. First, there are different types of files. A file's type is denoted with an extension, which classifies the file as containing data of a certain type. There are text files with the .txt extension, image files such as PNG and JPEG, data files such as CSV and PDF, as well as specific code files with the .java or .py extension. Not every program works with every file type. Most only work with a few that are related to the program's purpose, and if you've ever tried to open the wrong type of file with a given program, it can crash. Some might do both. There are lots of options when it comes to working with your files in a program. Most file systems store files in a tree or hierarchy structure. At the top is one or more root nodes. Under the root node, there are files and folders, and each folder can contain files and subfolders. Folders are often called directories in Linux and Unix systems, so you'll hear these words interchangeably in the course. A given file is identified through its path in the file system, starting with the root node. With this example file system, the path of the report.txt file is the C drive, home, author, desktop, reports, and the file name. Specifically, this is its absolute path. It contains the root node, the C drive, and has all of the information needed to locate the file on the computer. No context or relative location is required. A given path is either relative or absolute. A relative path for this file would be reports and then the file name. It's relative to the desktop folder. Another relative path would be desktop, reports, and the file name. This would be relative to the author folder. There is only one absolute path since it must contain the root node, but there can be several relative paths. Ultimately, the file system controls how each item is stored and how it can be retrieved on a given machine. There are many ways to interact with the file system. While you don't have to know much to click, drag, and create folders using a GUI, when you work with files using a programming language, it's important to understand the implications of file extensions and the differences between absolute and relative paths. Python's built-in OS module has lots of functionality for interacting with the operating system. In this video, we'll use it to navigate through a file system and display some files. To start off, we'll open the script file. I'll be using Sublime. Then, we'll import the OS module with import OS, and we'll set up some boilerplate code. Let's create a function for displaying the current directory that this file is run in. We'll call it display CWD, which stands for current working directory. The current working directory is the current folder we're working in. That's users, author, desktop, LinkedIn Learning. To retrieve the current folder path that we're in, we'll write OS and use the getCWD function. We'll save the output in a variable called CWD. Then we'll print it to the console. Let's call this function display CWD. This means we should get this file path in our output. Your output will likely be different if you're working with a different file path. To run the file, we'll use Python 3 and the file name, script.py. And in the console, we get the absolute path of the directory. We can also navigate to different folders in Python. Going back to our script, we can create a function called up1directory_level. In this function, we can use the OS module to change directories. We'll write os.chdir, change directory. For the input, we'll write .. and this will take us up one level in the tree. We'll be in the parent folder of where this script is run, the desktop folder. Let's call this function and then display the new current working directory. The new working directory will be the desktop. Let's run the script again. We go up in the tree to the desktop folder and then print out that new working directory. In our implementation, we hard-coded the .. path, but we could use any absolute path here on our machine. We can also use relative paths, but they should be valid to wherever this file is run. If we move to this file to a different folder or another location on our computer, we would get different outputs because the result depends on the current working directory. With Python, we can also list the files in a given folder. First, we'll create a function called display entries in directory. We'll have it pass in a directory name. Then, we'll use the OS module to access the scandir function. Scandir returns an iterator of all the objects in the inputted directory, including the attribute information. Since it's an iterator, we'll use the with keyword. For each entry in the directory, we'll print out its name with entry.name. This will print out all of the folders and files in the inputted directory. If we didn't add an input to scandir, it would print out the files in the current working directory. Now there is another function called listdir that can be used to print out a similar output. However, if more information about the file is needed, such as file type or its absolute path, scandir is better to use because it retrieves all of this information in a single scan, making it more performant. Let's call this function display entries in directory, and for the input, we have another folder in our desktop, the images folder. Let's print out the files in the images folder. With our program, the current working directory is the desktop. To access the images, we can use a relative path, images. Let's run it. We navigate to the desktop, and in the images folder, we have 5 images. We see all the files in that directory. If we open it up in the GUI, we see them here as well. With an understanding of how to work with different file paths in Python, you can begin to learn how to automate file and directory changes. With the OS module, we can find more specific details about a given file or directory. These details are things you might see available to you in a Finder type application, such as the last date modified, the size of the file, and when it was created. Let's take a look. We start off with a small Python file that imports the date time and the OS module. It also has some of the code from the previous video, as well as a small helper function for formatting a date, which will come in handy later. With a given file, we might want to find out when it was created. Let's add some functionality to the display entries in directory function and display when the entries were created. To retrieve the current status and other information about a given entry, we can use the stat function. This will return a stat result object that contains some metadata about a given entry. We'll save it in a variable called info. To display when the entry was created, it depends on the operating system. For Mac, we can use the st_birthtime attribute. If you're on Windows, you can use print creation time info.st_ctime. However, it is important to note that this will not work on other Unix or Linux systems. On other Unix systems, st_ctime will return the last time the file attributes or content were changed. On other Linux systems, there is currently not a way to retrieve the creation time. Now, no matter how the creation time is generated, we'll want this data to be formatted in the output. To do that, we'll pass it into our formatDate function. Again, if you're using Windows, make sure to use st_ctime instead. Let's call the function and see what this displays. As a reminder, this will scan the current working directory and display data about the files wherever this program is executed. This program will be executed in our desktop. We have a folder called Artwork, and that's where the data is that we want to scan. So for the input, we'll use the Artwork folder. This is a relative path from the desktop. Let's run the program in our desktop. And we get some information about our files and folders. We have two folders, SVG and PNG, a DSStore file, and a monster contact sheet. We can see these in the GUI as well. The .DSStore file is a hidden file since it starts with a dot, so that's something we will not see in our GUI unless we enable those settings. In addition to the creation time, we can also access other metadata about our files and folders. Let's display its last access time. We'll use our formatDateTime function, and the attribute is st_atime. We can also display the size. The size attribute is st_size. This will display the size of the file or directory in bytes. Let's run the program. Many of these files were accessed on May 6th, 2021, and have various sizes. We can also tell if a given entry is a file or directory with the isFile and isDir functions. Using scandir again, we'll create a function that only displays the directories. We'll iterate through the entries again, and if the entry is a directory or isdir, we'll print out the directory's name. Let's add it to the main function. This will display the subdirectories in the directory we give the function. We can also do the same for our files. Instead of isdir, we'll use isFile and print out the file's name. Now our program will print out the directories and the files separately. Let's run it. We print out the two directories, SVG, PNG, and the two files, .DSStore and monster contact sheet. This data can help you learn more about the files you're working with and eventually manipulate saved data programmatically. Filtering by file type or file name can become very useful when you want to work on a subset of files in a directory or on a drive. There are a variety of ways to do this in Python, but I find the simplest way is with the glob module. With Python's built-in glob module, we can filter for specific paths in a file system. Let's say we wanted to grab all of the ping files in a given folder. To start, we'll import the glob module and create a function called displayPings. Then, we'll use the glob function on the glob module to find all of the ping images. For the input, we'll use the wildcard symbol .ping. This will find all of the files of the ping type that are in the current working directory. Let's display these in the console and then call the function. To run the file, we'll write Python3 and the file name. These are the ping files. We have a monster1, monster2, monster3, a variety of ping images. In addition to filtering by file extension, we can also filter by file name. Let's say we only wanted to see the files of monster1, which are denoted with monster01. Now the sequence monster01 could be anywhere within the string, but we know it will contain the sequence. We can use the wildcard to filter for items that contain this set of characters anywhere in their file name. This will return any items in the images folder, including both files and directories, that have this sequence. If we wanted to, we could filter out the directories by using the isFile method from the OS module. For now, we'll just print the filtered items and then call the function. We'll run the script again, and we see only monster1 items. Now, what if we had other monster1 items in a subdirectory? We could display those using the iglob method. Iglob returns an iterator of the filtered items rather than a list. To make our function recursively search through the subdirectories as well, we can add recursive equals true to our parameters. When we look inside the subdirectories recursively, the item we get back will include the subdirectory name. We want to search for all entries matching this pattern, regardless of if the subdirectory name matches the pattern. This means we'll need to modify the filter sequence so that the subdirectory can be anything. To do that, we'll add a double wildcard and a slash. Let's call the function. We'll run the program again, and we see additional items. In the output, we not only see the monster1 items in the current working directory, but also any monster1 items in the subdirectories. With the glob module, we can easily filter down to just the items we want to work with. To automate file operations, it's important to be able to iterate through different parts of your file system. In the last video, we saw one way to iterate through the subdirectories of a given folder with the glob module. Here, we'll see how to walk through the different paths in your file system using the OS module. The OS module has a function called walk that can be used to generate the file names in a directory tree. We can walk top down or bottom up. For example, let's say we wanted to walk this current working directory. This directory has two folders. When we walk through the tree in a top-down format, the current folder will be first, and then it will return the subdirectories along with their contents. The current folder acts as a root of sorts and is at the top, and the subdirectories are returned second at the bottom. For a bottom-up walk, the function will return the files it finds in its subfolders first, before listing the contents of the path that was inputted into the OS walk. Let's try implementing this in code. We'll start by implementing the top-down walk function. This will use os.walk. For the input, we'll use the artwork folder. This folder will live in the same place that we're executing this Python file. OSWalk generates the items with the directory tree. On each iteration, it returns the current working directory path, dir path, the directories it contains, we'll call it dir names, and the files it contains, files. This is a lot of information for just one function to return. Inside the for loop, we'll print out the current directory we're at in the tree. We'll also print out the subdirectories that the dir path contains. Then, we'll print out the files that are directly in this directory. Let's run the program. If we scroll up, we can see how we walked through the tree. On the first iteration, the current working directory, artwork, is printed, along with its direct subdirectories, SVG and PNG, and the files directly in the folder, DSStore and the contact sheet. On the second iteration, the first subdirectory is printed, with its subdirectories and its files. This subdirectory happens to have another subdirectory in it, TN. On the next iteration, its contents are printed. Once the bottom of the tree has been reached for that subdirectory, the next directory follows, with its items printed. This walk starts at the top with the artwork folder and ends at the bottom when no subdirectories remain. To walk through these files in a bottom-up format, we can simply pass in an extra parameter to OSWalk. We'll copy the implementation of top-down walk and add in top-down equals false as a parameter. Let's see what the bottom-up walk looks like. We'll run the file again. The deepest directory is displayed first. Then, the program works its way back up to the directory passed into OSWalk. This can be very useful if you want to delete files, or you need to run some operation where the subdirectories must be modified before the root. It's important to note that OSWalk only returns a relative string path and name to the given entry. If we want more data about a given file, we'll need to use other operations from the OS module as well as other Python modules. Traditionally, Python has represented file paths using regular text strings. Paths have lots of information, and in order to retrieve that information, important functionality is spread all around the standard library, including in the OS, glob, and showtail modules. The pathlib module was introduced in Python 3.4, and it presents an alternative way of representing directory and file paths. It represents them as objects instead of strings. To use it, we can import path from the pathlib module. Let's print this directory's contents. To access the current directory, we can use the cwd function on the path module. This object is either a POSIX path or a Windows path object, depending on the operating system. With the entries, we can iterate through each entry and print out specific attributes. Entries.itterdir creates an iterator of all the files and folders in the current working directory. Each entry contains information about the file or subdirectory. It's an object, not just a string. We can print out the entry's name, as well as the parent directory path with entry.parent. Now, since entry.parent is a path, we can access it like a path and get its parent with entry.parent.parent. We can also use entry.stem to print out the file name without the extension. Entry.suffix gives us the extension separately. Let's call this function and run it. In the output, we get a bunch of information. We get the file's name, the file's parent, the file's parent's parent, the file name without the extension, and the extension separately. In addition to accessing the files in the current directory, we can also specify a specific directory with path. This input path can be relative to where the file is run, or it can be an absolute path. We can also print out the contents in the home directory with path.home. With each entry, we also get some other metadata about the file. To access it, we can do .stat. Let's run the code again. Entry.stat returns the same OS stat object that we've seen before, with size, last modified time, and creation time. So why use the pathlib module? The pathlib module provides an object-oriented interface to the file system. These functions are as efficient, if not more efficient, than many of the functions used in the OS module. The OS listdir function only returns a path in a string form. Other functionality must be used in order to get more information about the file. Using pathlib.path or os.scandir are preferred ways of getting file and directory listings because they not only retrieve the path, but also extra file attribute information. When working with files, sometimes you'll want to create a directory path to store log files or output files. Let's look at a few different ways we can create folders or directories in Python. One way is with the OS module. We can use os.makedir to create a new directory. We can name it by passing in the name of the directory as a parameter. We'll call it logs. This will create a directory wherever this Python program is run, since this path is a relative path. We also have the option of using an absolute path here as well. If this directory already happens to exist, then make directory will raise a file exists error. To handle this, we can wrap our makedir call in a try block. If the directory already exists, we'll print out a message instead of letting the error be raised. Let's execute this program and watch it create the logs directory. Looking at our desktop, there's our logs directory. We haven't put any files in it, so it's empty. Let's try running the program again. And we get an error. This time, the logs directory was already created. So instead of the program creating it again, we print the already exists message out to the console. Another way we can create directories is with the pathlib module. This time, we'll create an output directory. To start, we need to create a path object. We'll save it in a variable called dirpath. Then we can use makedir on this path object in order to create the path. It's important to note that the directory will not be made until makedir has been called. If makedir is never used, the directory will never be created. With the pathlib module, if the directory already exists, it will raise a file exists error. We could try to wrap this in a try, as we did with the os.makedir, but we also get the option to pass in an additional parameter to avoid this error. We'll write exist OK equals true. Let's call this function and execute our code. Looking at our desktop, we have an output directory. Let's try running the code again. No error, and still only one directory called output in our desktop. The output directory already exists, so it isn't created again. Whether you're using os.makedir or makedir on a path object, both return void, and both can be useful depending on which library you're working with. Let's practice working with file paths in Python. In this challenge, you will create a Python script that counts the number of files in your desktop directory. Your script should not only count the files directly in the directory, but also any files in the subdirectories. The count should not include folders, but only files containing data. We've explored several Python modules with various tools for interacting with the file system. Leverage these in your Python script. This challenge should take you around 20 minutes. Let's use Python to count the number of files in our desktop directory. One way to count the files is with the OS module. We can use the walk method. To start off, we'll have a total variable to keep track of how many files we've seen. Then, we'll use OS walk with the passed-in path to iterate through all of the subdirectories and files recursively. In our implementation, we only want to count the files, so for each file, we'll increment the total by 1. Once we've iterated through the tree, we'll return the total. Then we can call the function. I'll be running this file in my desktop directory, so it'll be counted as one of the files in my desktop. For the path name, we could use dot to represent this current working directory, or we could use the absolute path to the desktop. We'll keep this as a dot for now. Let's run our program. And we have 64 files in the desktop directory, including the files in the subdirectories. We can double-check this number by using a terminal command. We'll say find, use the absolute path to the desktop. We'll want to find the files, and we'll count them. And it's 64. It matches. Another option for counting the files in Python is to use scan_dir. Just like our other implementation, we'll have a total variable that starts at 0. Then, we'll use scan_dir to find all the entries directly in this path. If the entry is a file, we'll increment our total. Otherwise, the item must be a directory, so we need to search it to see the different files it has. Scan_dir only looks at the files directly in a given path. It does not recursively search through the subdirectories. With our count files function, we can add recursion. We'll increment the total by whatever our function returns with the subdirectory passed in. That's our entry. Then we'll return the total. If we wanted to use the pathlib module, we could apply the same logic as well. First, we'll import the module and set up a function. Just like the others, we'll have a total starting at 0. Then, we'll iterate through all the entries in the given path using iter_dir. Like scan_dir, this iterator will only provide us with the entries directly in this path. We'll need to add recursion in order to recursively search through the subdirectories as well. Let's call these functions and see what they return. To run the function, we'll use Python 3, and they're all the same number. Each function returned the same number of files in the desktop directory. Before accessing the contents of a file in Python, the file must be opened. A file can be opened in a few different modes, and the mode defines how its contents can be manipulated and accessed. R mode opens the file in a read-only mode. In this mode, the file's contents can't be changed, but they can be viewed. If the file does not exist, an error is returned. We also have the A mode for appending. You can use this mode to append onto the contents of a file. W mode opens the file for writing. If the file does not exist, Python automatically creates the file. By default, all files are read from and written to via text mode, but you can specify binary mode to read and write using binary. To specify binary, you can add the plus sign with a B. There is also one less common mode called X mode that creates the file if it does not exist. If it does exist, an error will be returned. Let's open a file using Python. Open is a built-in Python function that's a part of the Python standard library, so we don't need to import anything here. We'll create a new function called print content. Inside the function, we'll open up a text file in read mode. We'll use the open function and specify the file path and the mode, read mode. You can find this descriptions folder and its associated file in the exercise files of this course. For this example, the Python script and the descriptions folder are on my desktop. Back to our script, we'll save the open file in a variable called f, so we can run functions on it and interact with the file's contents. Let's read in all the contents of the file. We'll write f.read and save the output in a variable called contents. Let's display this to the console. Then we can close the file with f.close. While most of the time you only have to close a file if you're writing to it, it's always a good practice to close any files you open. This allows Python to manage the program's memory in an optimal way. Let's call this function and see what it outputs. To run the program, I'm in my desktop, and our script is script.py. In the output, we see the entire contents of the file. There are lots of different ways you can read in a file, and we'll explore them in later videos. But let's try another mode. Let's try writing to a file. We'll use the same file, but we'll use write mode instead, or W mode. Then we'll write a new description. After writing the description, we'll close the file. This will overwrite the current contents of the file. The old description will disappear and be replaced by this description. Let's call the function. In the output, we'll see a new description because we called the write function before the read function. We overwrite the file's contents before displaying them to the console. Let's run it. And there's our new description. In our desktop, if we click into the file, we'll also see that the content has changed. This isn't just something that happened in Python. It affected our files. Before we move on, we can refactor our code to make it a bit clearer using the with keyword. It makes it easier to quickly open a file, manipulate its contents, and automatically close it. It can be easy to forget to close the file when working with an unmanaged stream or resource, so using the with pattern is a great way to get around that. There are lots of different ways to read in a file's contents with Python. Previously, we read in a file's contents regardless of the size of the file. This is one option for reading in your file's contents, but if we only want to read in a certain number of bytes from the file, we can specify that as an argument. This will read in the first 10 bytes of the file. Let's run it. In the output, we only get a portion of the file's contents, the first 10 bytes. Another option is to read in a file's contents, but organize those contents with a list. We'll create a new function called print file content readlines, and this will use the readlines method to gather the file's contents. We'll use readlines on f and save the output in a variable called lines. This will have each line from the file as its own entry to a list. When we print out the lines, we should see a list of text where each entry is one line content in the original text file. Let's call this function. In the output, we have a list containing each line from the file. Each line has the \n character because this sequence represents a new line in the file. Now, maybe we don't want to display every line. We could print out a single line by accessing an index in the list. Let's say we want to print out line 1. Index 1 references the second item in the list. If we run the code again, we should get "these skills serve her well" this sentence. Let's run it, and that's what we get in our output. We also get the new line character translated as a blank line, or a new line. With read lines, we retrieve all the file's contents with a single call, and it's organized into a list for us. If you're working with a large file, it might take a while to read all the contents in one go. Another option is to read in the file one line at a time. Let's create a new function. In the implementation, we'll use the readLine method on F. This will return the first line of the file. If the file is empty, it will return the empty string. The file reader F keeps track of where we are in the file, so if the readLine method is used again, it will return the second line in the file. We can leverage this to iterate over the entire file line by line until the end of file character is reached, the empty string. Let's use a while loop. While the line is not the empty string, there is a line to be printed, so we'll print it. Then we'll go to the next line by setting line equal to f.readLine. And that's it. Let's call our function. This will print out the file's contents line by line. With the print function, it adds the new line character to the end of the statement, but we can eliminate this by adding the end option to our print statement. We'll say end equals the empty string. No new line added. Let's run it again. And there's the content. Python gives us lots of flexibility for reading the contents of a file. As a software engineer, you'll likely have to work with different types of files and data, not just plain text files. JSON is a popular format for representing structured data. It's commonly used by APIs as well as for other data transfers. JSON stands for JavaScript Object Notation, and the data is represented with name-value pairs. These name-value pairs are separated by commas. For more complicated values, objects are represented through curly brackets, and square brackets are used for arrays. Python provides a JSON module for working with JSON data. With the JSON module, we can load a given JSON file and work with it as a JSON object in our program. Let's create a function that displays a JSON object from a file. The file we'll be working with, monster.json, is on our desktop, the same place as the script we're using. We'll open up the JSON file as F, and this will automatically open the file in read mode. Read mode is the default mode for the open function. Then, we'll load in the file using the JSON module. We'll save the contents in a content JSON. From here, we'll print out the JSON and run the function. Let's execute the program. And there's our JSON data. So how is this different from just reading in the file as we've done previously? Since the JSON file was read in using the JSON module, we can use JSON operations on that content. For example, let's say we wanted to pull out the monster name in the JSON object and welcome the monster. The first few lines would remain the same so we can access the file's contents. However, when it's time to print out the name, we'll just pull it out of the JSON. We'll use our content JSON in the name attribute, monster name. Given our monster JSON, this will print out welcome spook, because the value for the key monster name is spook. Let's call the function and execute our program. Welcome, Spook! The JSON module makes it easy to parse JSON files in Python. Sometimes the data you're working with will be in a CSV format. Python provides a few different ways to pull out the necessary information and manipulate it as needed. One option is to use the CSV module. Working with a CSV file is pretty similar to working with a regular text file. We can open the file as usual, but we'll read it in a different way. We'll use the CSV module to create a reader object. We'll give it the file as well as a delimiter, which will be a comma. This is a comma-separated values file. Then, we'll iterate through the reader. For each row, we'll print out the monster name. The monster name is in the second column, so that would be at index 1. On the first iteration, this will print out the word monster name because that's what's on the first row, the column name. On the second iteration, it will print out the first monster's name, and it will continue to print out the monster names on the following iterations for each row. Let's see this in action. We'll call the function and execute it in our terminal. And there are the monster names. Depending on the index we put in for the row, we can see different column values. Another option is to use the name of the column to access the data. Instead of using a reader, we'll use a dictionary reader. We'll give it the file in the same delimiter and save it in an object. When iterating through each line, we'll use the name of the column to access a given row's value. Column that represents the monster's name is just monster name. We'll display what each monster is priced at. To retrieve the price, we'll use the name of the price column. That's just price. It's important to note that since we're using a dictionary reader, the column names will not get printed out. They'll be read in by the dictionary reader and stored. This means our first row here will actually print out the monster data. Let's run this function. And we get each monster with their price. Both of these options use Python's built-in CSV module, but often it can be useful to leverage the pandas library. Sometimes when you're working with CSV files, you'll want to analyze their data and run statistical operations. The pandas library is great for this, and it also has the functionality to import a CSV file. To use pandas, you'll need to install it because it's an external library that's not included with Python. To install it on a Mac, I'll use pip3 install pandas. If you don't have the pip package manager, you'll need to install it in order to run this command. Once pip and pandas are installed, you can import pandas into your Python file. We'll write import pandas as PD. To load in the data, we can use the read CSV function from pandas, or PD in our file. For the input, we'll provide the file name. The read CSV function returns a data frame, which is a special pandas data structure that we can display in the console. Let's call display CSV pandas. And there's our data. In this course, we will not be exploring pandas in too much detail, but if you're interested in learning more, I encourage you to check out some of the pandas courses on the LinkedIn Learning library. All in all, Python provides lots of different tools for reading in CSV files. Another common file type is PDF. To work with PDFs in Python, we can use an external library called PyPDF2. With this library, we can extract the title and author, encrypt and decrypt the file, as well as merge multiple pages into a single page. For this particular video, we'll be looking at how to use this library to read text from a PDF file. To start, we'll download the PyPDF2 with pip. On Mac, this is pip3 install PyPDF2. With it installed, we can use it in our Python application. Let's import the module. Import PyPDF2. In order to read a PDF in Python, we'll need to open it in binary mode, since a PDF is not a text file. The recipe book PDF is in our desktop, along with this script file. This will follow a similar pattern to our CSV reader. We'll create a PDF reader using the module. We'll save it in an object called reader. With this reader object, we'll be able to interact with our PDF file. Let's see how many pages it has. We can use the numPages attribute. We can also get other information about the document, such as its creator and creation date. To retrieve a given page, we can use the getPage method. Reader.getPage, and we'll retrieve page 2. The page object allows us to read and manipulate a single page with our application. Let's extract the page's text. We'll use extract text on the page object. Now, let's call the function. And we'll execute it in our terminal. The recipe book PDF has 16 pages, and we can see the content of the second page in the output. Back to our program, we can modify this so that every page's text is printed. Instead of printing out the contents of one page, we can use a loop for page and range, and we'll loop over the number of pages. For each page, we'll create a page object and print its contents to the console. Let's comment out these metadata lines and run the application again. And that's a lot of content. In the output, we see the text content for each page. It's important to note that the creators of this library have warned that the extract text method may not always return all of the text from the file. They have improved the algorithm over time, but it's not perfect. All in all, no matter what file type you're using in Python, there's almost always a library that will help you parse it and manipulate it. In this challenge, you will use Python to aggregate data from multiple sources. Your job is to find the most commonly used word throughout all of these text files, where each file is found in the same directory. We define a word as something separated by spaces or punctuation. In these text files, we'll only have periods and commas as punctuation, and they will not be counted as part of the word. Lowercase and uppercase words are counted as the same. Anything with a dash or quotes is counted as one word or phrase. You can find the sample text files in the exercise files of this course. This challenge will take around 45 minutes to complete. Good luck and have fun! Let's use Python to aggregate data from multiple sources and find the most common word. To gather all the text files in this current directory, we can use the glob module. We'll save a list of text files in their own variable, txt files. To gather the files, we'll use glob with star.txt. To keep track of the words we've seen so far, we'll create a tracker dictionary. Later, we'll use this to find the most common word. Now, whenever we see a new word, we'll add it to the dictionary as a key with the value 1. Whenever we see the same word again, we'll increment its value by 1. Let's iterate through the text files. For each text file, we'll open it in the read text mode. Then we'll iterate through it line by line. On a given line, we can split the line into individual words. The split method will return a list of words separated by spaces in the line. For each word, we'll want to normalize the input by removing the periods, commas, and converting it to lowercase. We can do that by using the replace and lower functions. Now we compare it with our dictionary. If the word is not in our dictionary, then we need to add it. We'll add the key word and the value 1. Otherwise, it has to already be in the dictionary, so we'll increment its value by 1. Whichever word has the highest value will be the most common word. Now, once we've done this for every word in the line, we can go to the next line. We'll use f.readline. After iterating through each file, we'll need to find the key with the max value in the tracker dictionary. We can use the built-in max method. We'll pass in the tracker, and the key will be tracker.get. This will return the max key, or the key with the maximum value. To find the maximum value, we can use max and pass in the tracker.values. These are the essential data points. Maximum key is the most common word, and maximum value is how many times it appears in our text files. Let's print them out. And that's our function. Let's call it. And the most common word is and. It appears 41 times. Now we can get some more details on how this algorithm works by adding a few more printouts. For example, we can print out how many text files are used. We can also print out the tracker dictionary itself. Let's run our program again. That's a lot of words. This program uses 4 text files and creates a pretty big dictionary. With Python, it's easy to work with multiple files at once. When developing a Python program, sometimes you'll want to output data to a file. We've already looked at how to read data from a file, but in this chapter, we'll explore writing data. The first step is to open the file in the correct mode, either W for write mode or A for append mode. Let's look at write mode first. To write data to a file, we can use the write method on the file object, writer.write, and we'll write hello. This will create the num series text file and give it the content hello. To make this a little more interesting, let's say we want to write the numbers 0 through 49 to this file. To do this, we can create a loop for x in range 50. For each number, we'll create a string that we'll write out to the file. We'll give it the number and a new line character. Then we'll write the content, writer.write content. This will write out the numbers 0 through 49, where each number is on its own line. Let's call the function. We'll run it in our terminal. In our desktop, we can see the num series text file. If we open it up, here are the numbers 0 through 49. In this example, we generated a piece of content and then wrote it out to our file. Another option is to generate a larger string with all of your content and then write out to the file once. It's up to you whether you want to slowly build up your file or generate the content all at once and then perform one file interaction. However, it's important to note that when we reopen a file and write to it, it erases any content that previously existed in the file. In our example, we wrote to the same file multiple times, but we were using the same file object. If we reopened the file in write mode and tried to write to it again, it would erase our number series. Let's try overwriting our content. We'll overwrite it with the numbers 50 to 99. Let's call the function and execute our program. Let's see if the file changed. We'll open it up. And now we have the numbers 50 to 99. We overwrote the previous content. Now, if we wanted to append these numbers instead of overwriting the previous content, we could use append mode. All we have to do is change W to A. This will open our file in the correct mode to append the items. Although we don't have to, we'll also change the name of our function so it makes a little more sense. Now we're appending content. Let's execute our program. If we open up the file again, our file has the numbers 0 to 99. With Python, we get many useful methods for writing data to files. Moving and renaming files are common operations in Python programs. For example, you may want to move current files into a separate directory to make space for new files. You also might want to rename a set of files to reference the date or year they were created in. When we move a file, we change its file path. Instead of home desktop example.png, we might move it to home desktop homework example.png. In changing its path, we move the file to a new path. However, if we changed home desktop example.png to home desktop example1.png, we've renamed the file. Technically, we've moved it to this new file path, but in Python, we consider this operation renaming the file. We can rename a file using either the OS module or the pathlib module. For the OS module, we can use the rename method. The first input will be the current name of the file. In this case, we're going to rename monster1.png. The second input will be the name we'll want to rename it to. In this case, we'll want to introduce an underscore between monster and 01. We're using a ping file here, but this operation will work for any file type. For the pathlib module, we can create a new path object and use the rename operation. Like the OS module, we can rename any type of file with pathlib. Let's call these functions. To execute our program, we'll go to the terminal. If we look in our desktop, we can see the monster1 and monster2 have been renamed as expected. Now, if we want to move files to another location, we can use the showtail module. With showtail, we can move files from one folder into another folder. In this case, we'll move all of the images into a ping folder. We can also use the showtail.move function to move a single file. All we have to do is provide the appropriate input. Since our monsters are now in the ping folder, we'll grab monster3 and put it into an SVG folder. The SVG folder does have to exist in order to move a file there, so we can create it quickly using the OS module. Now we'll have the ping items in the ping folder and the SVG image in an SVG folder. Let's run these. If we click into these folders, the files were moved as expected. With Python, we can automate file operations using move and rename functions. The showtail module also provides ways to copy files. To copy a file from one folder to another, we can use showtail.copy. The first input is the file we want to copy. In this case, it'll be monster01.png. The second input is the folder we want to copy it to. In this case, we'll put it in the images PNG folder. It's important to note that this function only copies a file's contents and permissions. Other metadata like file creation time and modification times are erased. To keep all the metadata when copying a file, we can use the copy_to function. For this example, we'll copy monster2. And we'll put it in the same place, images PNG. Let's call these in our program. And we'll execute it. If we open up our images PNG folder, we can see monster1 and monster2 have been copied. If we look at the metadata for each ping file, we can see some differences. Monster1 was modified today, whereas monster2 was modified a couple years ago. In addition to this, we can also copy directories with files. If we want to copy a directory, we can use showtail's copy_tree function. This operation is recursive, so it will copy everything, including those subfolders. An important note about copy_tree is that the destination directory cannot already exist. Otherwise, you'll get an error. Let's try it out. With the Finder, we can see the new backup images directory with all of the files from the images directory in it. This is a good operation if you need to back up your data. If you're working with tabular data, sometimes it can be useful to output it to a CSV file. With the CSV module, we can write data to a CSV file in a few different ways. If your data is stored as a list, one option is to use the CSV writer object. In order to do so, we'll need to open the file in write mode and create a writer object from the file. With the writer object, we can write individual rows to the CSV file. The data just needs to be in the format of a list. When this is written out, each item in the list will be in the CSV as an individual entry. These are the headers for the CSV. Let's add some data rows. We'll add an office chair. The ID is 41, the category is furnishing, and there are 10 in stock, each priced at $85. Let's add some more data. Great! Let's call the function and save the data out to CSV. We'll run it in our terminal. If we run ls or dir on Windows, we can see the new CSV file, products.csv. We can take a look at what it contains with cat products.csv. There's our data. Now, if your data is stored as a dictionary, the CSV module also provides options to write it out as a CSV. Similar to before, we can open the file in write mode. Then, we can create some dictionary data and set up a dictionary writer to write it out to a CSV. When creating a dictionary writer, we have to give it a set of headers. The headers are necessary because we need to match what's in a given dictionary to the appropriate CSV column. Let's write out the headers to our CSV. Then we can add an item. We'll write the header with write header. We'll also create our item. And then write it out to our dictionary with writer.writeRow item. Let's call this function and execute our program. We can look at the new CSV with cat maintenanceproducts.csv. And there's our ladder entry. Now, what if we wanted to append to the products.csv file instead of creating a separate maintenance file? When opening the file, we can change the mode to append and use the products.csv file name. We'll still need the headers to set up the dictionary writer, but we'll need to add the category back in. We will not want to reappend the headers, so we'll comment out the right header line. Then we can add the maintenance category to our item. Let's run the program again. The ladder item has been added. With Python's CSV module, we get some handy functions for working with CSV files. JSON is one of the most popular formats to serialize data. After creating dictionary data with Python, you may want to save it to a JSON file. Here, we start off with some sample code that will convert a given set of monster attributes into a dictionary object. Each monster product has a name, title, price, and level of scariness. We can use this function to generate a dictionary for a given monster. Let's try it. Here, we create Philo, who is a baker by day and techie by night. It's priced at 29 and has a scariness level of 3. Let's generate a few more items. To write these dictionary objects out to a JSON file, we can use the JSON module. We'll open up a new file in write mode and then write out the dictionary data in a JSON format. We can use the dump function to write the data in the correct format. Let's call this function with a list of our dictionary items. That's monster 1, 2, and 3. This will create a file called monsters.json with our dictionary data in it. Let's run it. If we display the file's contents, we can see our data displayed in the terminal. It's in a JSON format. This looks great. With the JSON module, we can easily save data to a JSON file. Let's practice automating tasks using Python. In this challenge, you will create a program that reorganizes the photos in a given folder by renaming them. Many of the photos have different names, but we want to rename them so they all follow a common form. For example, each photo should start with the year, month, and day it was taken. We can use the creation date on the metadata of the photo to determine when it was created. Then, it should have whatever the current name of the photo is. The photos could be of type PNG or SVG. For the photos, you're welcome to use your own or use the samples provided in the exercise files. For this challenge, expect to spend around 30 minutes completing this. Good luck and have fun! Let's create a program that organizes our photos by renaming them. To start off, we'll create a function called Organize Images. It will take in an image folder for where the images live. An image could have the file type PNG or SVG. So let's enumerate those in a list called file types. Now that we've defined the image file types, we can begin to iterate through all of the images in the image folder. We'll do this using the pathlib module. Let's import it. To find all the entries in the image folder path, we can use iter. We'll write for path in path with the image folder, iter. Now that we have access to each path, we can filter out the invalid entries. We'll check if the path is a file and if it's the appropriate type. In order to watch the processing happen in the console, we can print out the name of the file with path.stem. We'll log out what we're doing, renaming file with this particular stem. This will print out the file name without the extension. To organize our files, we'll want to rename it using the file's creation date. The first step in this is retrieving and formatting that creation date. We'll separate it out into its own function. Def generate creation date. To retrieve the file's creation date, we can use path.stat. We'll save it in a variable called statResult. StatResult is an object containing various metadata about the file. Since we're using a Mac, the creation date lives at the stBirthTime attribute. On Windows, it would live at stCtime. On other Unix systems, st_ctime will return the last time the file's attributes or contents were changed. If you're working with another Unix system, that's good enough for now. On other Linux systems, there's currently not a way to retrieve that creation time. Your next best data point, like with the Unix systems, is the last modification time. This information can be found with st_mtime. Now that we have the date, we need to format it to the correct format: year, month, and day. We can do this with the datetime module. We'll create a UTC timestamp with the date and format it accordingly. Now we can use this function for our image path. We want the new path for the image to be the date, original file name, and then the extension for the file. We can create a new path to represent this. We'll have the date with the path.stem and the suffix or the file type. This will place the code in the same folder of wherever we're running this Python program. To keep the file in the image folder, we'll need to add the image path at the beginning as well. Great, there's our new path. To rename the image file, all we have to do is call rename on the original path. And we'll pass in the new path. This will rename the file. Let's call the function. We'll pass in the images folder. Let's execute it. It looks like we might have misspelled something. Creation date should have the underscores. Let's run it again. These errors happen from time to time. And another misspelling. It looks like we forgot the I. Let's try it again. That was quick. We renamed all of our files. Here they are in the Finder as well. We've organized our photo collection. Archives are an easy way to package several files together for data storage or data transfer. With Python, we can create many different types of archives, including zip files. Zip is a common archive format that supports lossless data compression. To create a zip archive, we can use the zip file module in Python. For the function, we'll call it createZip, and we'll pass in a list of files that we want to put in the archive. To create the zip file, we'll follow the same pattern as we've seen previously, where we open up the file and then write to it. We'll use the zip file module with zipfile.zipfile. Then the name of the archive we want to create, we'll just call it archive.zip. We're going to write to this archive, we're going to create it, and we'll refer to it as archive. For each file in our file list, we'll write it out to the archive. This will archive all of our files. Now it's important to note that this will copy the file to the archive. It will not delete the file outside of the archive. Let's call this function and test it out. We'll create a list of file names and then pass them to create zip. Let's execute the program. If we go to our desktop, we can see the archive.zip. This is what our Python script created. If we click on it, we've opened the archive and extracted the files. There they are. Since we already had a ping folder on our desktop, this one got named ping2. Similar to writing text files, the write mechanism will overwrite any zip file of the same name. If you want to append to a zip file instead of overwriting it, all you have to do is change the mode to A, or append. So we'll copy this function, change the mode to append, and rename it. Now we have a function for appending to zip files. The zip file module works great for archiving files, but if you need to archive nested directories, we'll need to use a different module, specifically the showTel module. As mentioned before, the showTel module is great for working with collections of files. With showTel, we can create an archive with nested directories. To create the archive, we'll call makeArchive from the showTel library. The first argument will be the archive's name. We'll just call it directory archive. It will be of type zip, and we'll want to archive that directory path. Let's test out this function. We'll give it our SVG directory. This directory has nested directories, 1, 2, and 3, each with their own files. Let's execute our program and watch this be archived. In our desktop, we have a directory archive. Let's open it up. With Python, we have flexibility to create zip files in many different ways. Whether you want to read a zip file or extract all the data from an archive, it's important to be able to access your files in Python, no matter the format. Let's look at how to read a zip file and extract files from it using Python. To work with zip files, we can use the zip file module. To get information about a zip file, we can create a zip file object and open it in read mode. We will read the archive.zip file, and we'll refer to it as archive in our program. When reading a zip file, we can see what files are in it with archive.namelist. Let's print it out to the console and see what's in our archive. We'll execute it in the terminal, and there's two files, description1 and description2, both text files. Given these file names, we can use one of them when reading the zip file to get more information about that file. Let's say we wanted to get more information about description1. We'll open up the archive in read mode. Then we can use the archive to access description1. We'll use archive.getinfo and pass in that file name, description01.txt. Let's see what info we have access to. And we'll move this to the top so all of our functions are together. Then we'll call the function. We get the file name, the compression type, the compression size, the file permissions, and the file size. We can access each of these directly in our program by accessing the attributes of the file info object. Now, if we want to work with the file directly, we can open it using the zip file object. We'll open up the zip file as usual. Then we'll use the archive to open the description file. All we have to do is call open on the archive. Now we can directly operate on the file. Let's read it. Here, we are reading the description01.txt file. Let's test it out. And there's our content. This is the content in the description01.txt file. Now we also have the option to extract the file. We'll open up the archive in read mode and then use the archive to extract a single file. myarchive.extract, and then the file we want to extract. Let's try extracting that description file. We'll call our function extract file. The archive is archive.zip, and the file description01.txt. Let's try it. In our desktop, we now have the description01.txt file. The file was abstracted. Now, if we want to extract all the files, we can use the extract all function. We'll access the archive with extract all, and we'll put them into a folder called extracted files. Let's try it. In the desktop, we now have a folder called extracted files. If we click on it, we can see description 1 and description 2. With Python, we can easily work with zip files to get important file and directory information. tar is another common archive format that supports gzip, bzip2, and LZMA compression. We can use the tar file module to work with tar files in Python. Let's read a tar file with Python. Tar file objects follow the same pattern as other file-like objects. We can open them in a specific mode using a with statement. If your tar file happens to be compressed, you'll also need to pass in the compression mode. This mode would be gz for gzip compression, bz2 for bzip2 compression, and xz for LZMA compression. The file we're working with has gzip compression, so we'll use r:\gz mode. With the tar file open in read mode, we can start to retrieve information about the archive. For example, we can retrieve all the file names with the getNames function. We'll access the tar.getNames. We'll print these to the console. We'll also clean up our comment a bit. Now we can also get information about a specific file using getMember. tar.getMember, and then the item we want to get information about. In our case, it's descriptions, description01.txt. The getMember function will return a tar info object that contains the file's name, size, and permissions, along with some other metadata. Let's display those. Let's call our function. We'll get to see what's in the archive, as well as some more information about the description01.txt file. It looks like we have a descriptions folder, along with some text files. The description01 text file is about 316 bytes. Back to our program, We also have the option to iterate through all the entries in the archive. We can use get members. This will loop over all the items in the archive, printing out the name, size, and mode. Let's try it. Get members retrieves all the files as well as the directories. If we want to access the contents of a file inside a tar archive, we can use the extract file function. The extract file function will only extract the file for reading and writing. It will not extract the file permanently. Instead, it returns a file-like object that can be used for working with the file inside the archive. Since it is a file-like object, we can open it using that same withOpen pattern and read its contents. Let's try it. Let's display the contents of the file. We'll call the function and execute it in the terminal. There's the text in the file. If we look in our desktop, we can see that no files have been extracted. With the tar module, we can easily open and read the contents of files in a tar archive. When you need to transfer several files, it can be useful to store them in an archive. Tar is a common format for archiving a series of files, and we can use the tar file module to create an archive. Let's say we want to create an archive of a few monster-related files. This will follow that same withOpen pattern. We'll open the tar file in write mode, and this will create that archive. From there, we can use the add function to add each file. Like with many write operations, this will overwrite any archive.tar file that already exists. To append to an existing tar file, we can use the append mode. We'll append the monsters card03.png. This will add on to the tar archive without overwriting the previous content. Let's call these functions. We'll create the archive and then append to it. Here's our tar archive. Let's open it up. Inside, we have the PDF, PNG, and the CSV file. If you want to write to a compressed archive, you can add on the mode with the compression type. GZ for gzip compression, BZ2 for bzip2 compression, and XZ for LZMA compression. Currently, append mode is not supported for compressed archives. If you want to add files to a compressed archive, you can overwrite the current archive or create a new separate archive. Now, if you happen to receive a tar archive and want to extract files from it, you can do so with the tar file module. This will follow that same withOpen pattern. The default mode for open is read, so we won't specify a mode. To extract a file from the archive, we can write tar extract and then the file we'd like to extract, monsters card03.png. Let's call the function and extract the file. Before we extract the file, let's take a look at our desktop. We'll delete the monstercard.png so we can see it extracted from our archive. Let's run the program. Going back to the desktop, there's our monster card. It was extracted from our tar archive. To extract all the files in the archive, we can use extract all. We'll open the tar file and use the extract all function. The value that's passed into the function will be where the files are extracted to. In this case, it will extract them to a new folder called extracted monster files. Let's run it. If we go to the desktop, all the files have been extracted to the extracted monster files directory. Temporary files can come in handy as a quick backup or storage for an intermediate state. We can create temporary files in Python using the temp file module. Temporary files can come in handy as a quick backup or storage for an intermediate state. We can create temporary files in Python using the temp file module. The temp file module automatically deletes the temporary file once the file is closed. Let's take a look at how it works. To start, we'll import the temp file module. To create a temporary file, we can open a temporary file object. We'll open it in write and read mode, W+. This looks a little different than the previous pattern because we don't give the file a name. Since the file is temporary and it will be deleted after the file is closed, there's no need to provide a name. Let's write out some content to our temp file. tf.write. In order to read the file, we'll need to go back to the beginning of it. tf stores a pointer to where we're currently working in the file. Since we've written to the file and there's no other content after that write, tf has nothing to read. To go back to the beginning, we can use seek. Then we can read the file. This will display what we've written on line 5. Let's call the function. We'll run it in the terminal. And there's the content. If we look in our desktop, no new files have been created. Now, during the program's execution, a temporary file could be placed in one of many different locations. It depends on the operating system you're using. We can find out the location by using the getTempDir function from tempFile. Let's run the code again. It looks like my default location is the var folder. This is typical for Macs. With Python, it's easy to create temporary files while your program is executing. Congrats on finishing the course! Now you know how to use Python to automate many different file operations and work with several files at a time. As a part of this course, we discovered how to read, write, and append to files of different types. We also looked at how to walk through the file system programmatically, iterating through files, directories, and subdirectories. This allowed us to easily rename, move, and manipulate multiple files at a time. We also explored how to save data from a program in text and CSV formats, allowing us to store data created from a Python program. To continue your learning with Python, I recommend checking out my Learning the Python Standard Library course to get more familiar with what's built into the Python language. The Python Data Analysis course will also help you get more familiar with pandas, NumPy, and other technologies that let you analyze data from external sources in Python. Thank you for watching this course. I really enjoyed creating it to help you automate common file operations and save data out from a Python program.